Hello, everyone. I'm Dane Christensen, the Digital Marketing Manager at GridGain Systems, and I want to thank you for attending today's webinar, How to Choose the Right In-Memory Solutions for Your Apps. Your presenter today is Nikita Ivanov, the founder and CTO of GridGain Systems, as well as a member of the Project Management Committee for the Apache Ignite project. Nikita has over 20 years of experience in software application development, building high-performance computing and middleware platforms. He was one of the pioneers in using Java technology for server-side middleware development, so you'll certainly be learning from one of the masters today. But before we get into Nikita's presentation, I wanted to cover just a few housekeeping items for you. First, you can expand your slide area by clicking on the Maximize icon on the top right of the slide area or by dragging the bottom right corner of the slide area. At the bottom of your audience console are multiple application widgets you can use. If you have any difficulty, please click on the yellow Help widget, which covers common technical issues. If you have any questions for Nikita during the webcast, you can click on the red Q&A widget to submit your question. Nikita will answer questions during the Q&A section at the end of the presentation. It's possible we may not have time to get to all the questions during that time, but if he isn't able to get to your question, we will certainly follow up with a response by email after the event. A copy of today's slide deck in PDF format is available in the green resource list widget. There you'll also find other valuable resources, including comprehensive feature comparisons between GridGain and Oracle Coherence and Hazelcast. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier or from the GridGain website. So with that, we're ready to turn the floor over to Nikita Ivanov. Nikita?
Dane, thank you very much for introduction. Good morning or good afternoon, everybody. Thanks for joining this webinar. And what we're going to be talking today is how to choose the right in-memory product and solution for your apps. By the way, my name is Nikita Ivanov. I'm a founder of Original GridGain Project and Apache Ignite PMC member. So it's the way I'm usually try to do this presentation is not really kind of bombard you with, line by line item comparison between two products or three products, but rather talk about all other issues surrounding the selection of in-memory solution. What is the memory? What are some of the key features? What are some of the myths about a memory computing? It's kind of important to understand as well, and talk about the different categories. So once again, as Dan mentioned, you can get all the detailed comparison from either our website at GridGain.com or ApacheIgnite.org. You can get it from different companies as well. So if you're just looking for a kind of line by line, feature by feature in a laundry list, you can get them very easily. And I actually advise you to get them because they'll give you kind of a detailed list of, feature by feature if you need one. But today I really want to concentrate on practically everything else but feature by feature comparison. Naturally, every vendor will brag about their performance metrics and how to beat everybody. So it's a fairly biased if you just go feature by feature. But you can always get them. They're available on either our website or other products' websites. So what we're going to talk about today, as I mentioned, we talk about a little bit of introduction of IMC, talk about some of the myths about in-memory computing, some of the product categories, some of the key features you want to really look at when you're selecting a product, and some of the interesting use cases and applications that I've seen in my life. So let's start with introduction. And by the way, as Dane mentioned, we're going to have the whole section for the Q&A, so don't worry if you have a question. Again, I'm assuming that you guys on this webinar probably know what in-memory computing is because you're kind of looking for the selection of product. But very, very quickly, I always want to set the stage level. So in-memory computing is a technology that uses high-performance distributed memory systems to compute and transact on a large scale data sets we call them big data in real time. And typically the key here is that real time means orders of magnitude faster than is possible with disk or flash-based systems. And the key phrase here is literally orders of magnitude faster. In memory computing, the number one reason to use in-memory computing technology is to get the performance and the scalability. Nothing else can give you dramatic performance jump like in-memory computing. Nothing else. Flash or any, many years ago, we had a project where we tried to basically rewrite application from Java to C, from C to assembly even, use a different, custom-made hardware, any type of improvements you can make to application will never get close you to the performance advantage you can get by moving to memory computing. One of the recent proof of concept we did for one of the largest banks in the world, using the Apache Ignite, on 10, just to give you an example, on 10 commodity blades, we were able to achieve, with 10 commodity blades and 1 terabyte of RAM. This is the setup. 10 commodity blades and 1 terabyte RAM across all of them, on a simple cast application for the risk management. We were able to achieve 1 billion transactions per second. Think about this, billion full two-phase commit transactions per second on literally 10 commodity blades, terabyte global RAM. So this type of performance is unachievable in any other way. It doesn't matter what language you use, what database you use, what hardware you can use. There's no hardware today to give you this performance increase without moving stuff into the memory. So why all of a sudden we talk about memory computing just in the last maybe 3 to 5 years? Obviously there's nothing new about memory computing. From day one we starting to use our computers, we know when you put stuff in RAM versus in remote in external disk systems, things go dramatically faster. The key was price. This is a chart here on the slide, by the way. It shows the price per kilobyte for hard drives, for flash, and for RAM. It was really cool, and it's really indicative of what the current interest in memory computing is, that the price of RAM, of DRAM, is going down 30%, almost 30% year over year. And this, if you see this on the chart, this blue line on the bottom line, the blue line, is the hard drives. The yellow line, the flash, and the green line is the DRAM. And that's a pretty indicative that have basically all the lines kind of following the same trajectory down. And somewhere around 2010, 27, 28, 29, 2010, those years, the pricing point kind of broke through some kind of psychological barrier, and RAM became really, really available and affordable. Today's terabyte of RAM costs about $25K. It became really, really affordable. So, kind of dovetailing this conversation, I won't spend too much time, but it's always fun to look at historical perspective why memory computing is important. And it doesn't really directly translate to selection criteria, but I do always like to talk about this because it gives a perspective. So if you look back in history, in the 50s, we started with that's where the era of non-volatile external storage really began. And Remington, actually, out of all companies, developed the first, system Uniserve on the magnetic tape, on the tape drive. And that's essentially where we first got our, ability to store data elsewhere outside the computer. So when the computer is powered down, data is not lost. In the 60s, hard drives came around, and in the 70s, IBM released, famous Winchester system, System 340, and the era of hard disks started, and they became very economical. What happened at the same time? The SQL revolution happened at the same time, and we basically ushered the era of the structured data, of a standard query language for this data, and a very cheap, relatively cheap, affordable external storage. 90s and 2000s, early 2000s was the time of flash development. Toshiba introduced, I think, flash technology late 80s, 1980s, and but essentially by the beginning of 2000s, flash was becoming the dominant storage layer. If you look at your phones, you look at laptops, look at your iPad and tablets, and plenty other devices, flash is one of the major, the only storage medium. But the flash has always been a temporary stopgap solution. It's not going to be the end of it. It's basically kind of stopgap transient solution between the hard disk and the RAM. And by all accounts and by all experts and analysts, 2010 and up and forward is the era of in-memory computing. And several things happening at the same time. 64-bit CPUs now allow you to address a sizable amount of RAM from one computer. The price drop for DRAM, 30% year-over-year, really makes the RAM now affordable. What else is happening is, as we all know, the NoSQL revolution is happening. And as everybody's saying, majority of the data we're collecting going forward will be unstructured. And most of the in-memory computing systems are NoSQL in their design that support SQL and NoSQL paradigm nicely. And that makes the system much more adapt to these new types of data we collect rather than traditional SQL systems on the disk. What's also interesting, and the reason I'm actually talking about all this historical look back, is that if you think about in-memory computing or storing data in memory is the last frontier of the storage. Now, it may sound provocative, but think about it. We moved from magnetic tapes to hard disk, basically magnetic things spinning in a vacuum. And then we remove all the mechanical devices and move to the flash, which is essentially a type of RAM that's external and non-volatile. And now we move to RAM, and a year or two we're going to have our laptops with non-volatile RAM already. It's available today. Think about what's next. Where else can you go to store your data in the computer systems as we know them today? About the only place is the on-chip, on-CPU cache, but it's very small because of the physical limitation. It's about 2-3 times faster than the RAM itself. So it's not an option. So memory or in-memory storage is really the last frontier in terms of the data storage as we know it, unless we fundamentally change our computer architecture. And that's why everybody's so excited about in-memory computing, because it's not a stopgap measure. It is the fundamental last final frontier and how we're going to store data going forward. 10, 15, maybe 20 years from now, it's probably going to be the same. RAM will become faster and cheaper and faster, but fundamentally, that's the way we're going to be dealing with our data. We're going to be stored in RAM, processing it in RAM going forward. So another interesting way to look at on the performance, and that's actually a very important, very important point to understand where does performance of memory computing come from. We talk about in-memory systems, and that's becoming a little bit more important also selection, because we kind of remove some of the incorrect thinking about in-memory. But we talk about in-memory systems. We're not talking about in-memory only. Almost every in-memory, almost every system that you see built with in-memory computing would have disks. So when we talk about a memory computing system, we talk about memory first, disk second, versus traditional systems that were disk first and memory second. Let me explain. So when we have a disk first architecture, our traditional, something we've been doing for the last 50 years, in this system, or this architecture rather, the data is stored on the disk. And then almost every database or application will have a small amount of cache in RAM. And the cache really used to store a frequently accessed data elements in RAM. So that when you need it, you don't have to constantly go in database, fetch it, process it, and drop it. You have it basically in RAM where your application is. And that was a very traditional approach. RAM was very small, it was very expensive, and disks were plentiful and a lot cheaper, so that made sense. Naturally, in-memory computing turned this paradigm upside down. In-memory computing systems use distributed RAM to store most of the data, if not all of it, and use disks only as a backup storage. Naturally, today, memory is a volatile memory, yet still. So for that, you need to have some kind of other systems where you can synchronously or asynchronously store data from RAM, just for safety reasons if you need it. So disk really used just for that in memory system, just for the backup. If you think about these two differences, this is the fundamental reason why in-memory computing is so fast or can produce such a performance in a giant leaps in performance. Think about this first architecture. Let's imagine your application needs to get a piece of data. Just to think through the chain of calls it needs to make. So application has to make an application call to the operating system I/O. The operating system I/O makes the call to I/O control, and I/O control then connects, communicates with the disk, and the disk has a seek time. It finds the piece of data, block of bytes, and sends us all the way back. After this, marshalling in demarshalling, because obviously your, for example, Java application doesn't speak with the byte streams, it speaks with objects. So on the application level, somebody needs to marshal and demarshal this data back and forth between the object and the bytes. That's pretty long trip with different subsystems and whatnot. Now, when you have data in RAM and you have a memory system, when your application needs to get access to a piece of data, all it needs to do is the pointer arithmetic. There is no marshalling, there is no demarshalling, there is no OS I/O, there is no controllers, there is no seek time, there is nothing. All your application have to do most of the time is to literally point to a different location in RAM. And there's object there that is in exactly the same format you're expecting. This is the fundamental reasons why if you do the memory computing right, you get this dramatic performance benefits. Not only because RAM is fast, of course RAM is faster than disk, but because it induces the different semantics in how you process the data. That's a very important consideration to kind of keep in mind. So let me talk about some of the quick myths about memory computing. Again, those will kind of help you kind of round your understanding of what's true and what's really not true today about memory computing. So too expensive. The first thing everybody says about memory computing, even if you guys use the memory computer today, I guarantee you that most of you guys saying that, well, it is pretty damn fast, but it's expensive. And I would argue that it's not. It's relatively expensive. Yeah, it's not free. Like, for example, the spinning disks today is essentially free. The RAM is still not free. It still, costs some money. But, it has come down dramatically in price in the last maybe 5 years. I already mentioned to you that in today's prices, the terabyte of RAM costs about $20K. And it's the price of a used car. Just to give you perspective, just a few years back, the entire working set of Twitter, for example, was about 7 terabytes. Working set of Twitter essentially is about a week of tweets with all the metadata information attached to it, right? So for the price of the pretty well-loaded Tesla, or new Tesla, about $150K, you can buy about 7 terabyte of RAM and have the entire working set of Twitter be in RAM and have any kind of processing, any kind of analytics, a literally sub-second on this data side. So it is not an expensive proposition. 10, 15, 20 years ago, yes, it was. And it was only available for, high-end financial services, DoD, three-letter agencies and whatnot. Today, it is not, the cost is not an issue for memory computing, that's for sure. We also basically have the new types of memory coming up that trying to play on a different ratio of speed and performance, and I would say speed and price. There's a memory channel systems, there's a storage class RAM, there's a non-volatile that Intel just came out with the PDX point architecture. What we're going to be seeing in the future I mean literally sometimes by end of next quarter, sometimes in a year, sometimes in 2 or 3 years, we're going to see proliferation of different types of RAM. The fastest from what we have today, DDR4, and it's probably going to be most expensive. But when we have, some other RAM types, it will be basically speed of DDR3, but maybe cost 5 times cheaper. Actually cheaper, maybe, than today's flash. And it's going to be a non-volatile RAM. The RAM that basically you can unplug your computer, plug it back, all that is still there. So going forward, and that's how it's actually happening today already, we're going to see a lot more choices in RAM. If you don't need this dramatic performance of the fastest DDR4, you can basically get something, step down like DDR3 performance for a lot less money, and for example, get the non-volatility to it as well. So RAM is not expensive today, and it's going to become much more flexible in terms of the price points going forward for sure. Non-durable. Again, if you're just looking for a standard DDR3, DDR4, yes, RAM is not durable. You have to have some ways in your in-memory computing systems, in-memory computing products to deal with this. And by the way, this is now one of the first things I want to mention to you. When you select the products, really look deep at durability. Because not every one of you will be jumping a new type of memory, such as non-volatile RAM. So for most of us, for the 2 or 3 or 4 years from now, we're still going to be using the volatile RAM, DDR4. And for those systems, you have to have some durability. The best products out there will provide you multiple options. You obviously can, keep multiple copies of the same data in the cluster. You can use disk. You can use flash through a direct interface to flash. Somehow, you have to have an option to have a durability. You don't need it every time, by the way. There's a plenty of data sets that can be kept in memory and not have any kind of durability associated with them because they can be recreated or they're temporary in nature. But sometimes you need a durability. And, most of the mature systems today, such as InMemory, for example, or GridGain, would have the whole set of options for you, and you can pick one that works best for you. Another thing I want to talk about is the flash is fast enough. It's actually not a myth, but it's rather, significant misunderstanding. Flash actually is fast. It's faster than a disk, but not by much. But on the reads, the seek time is a lot smaller than the disk. What's interesting that everybody is missing about the flash is just as fast as a disk. It's still a block level device. You still deal with flash predominantly as a file. So you have remember the slide that I showed you, different cold chains between memory first and disk first. You still have all the slowness of this long cold chain between application, operating system, IO controller, and a device. What flash does is that seek time of a device is smaller on a flash. There's no moving parts. It's basically just, it's all on the chip, the memory chip. But then you have all other things as well, marshalling, demarshalling, all this chain of events. So flash is rather faster than disk, but obviously dramatically slower than the RAM. And it really depends on the applications. If you're just looking for 2-3 times faster storage system, flash is a great option. It costs almost the same as a spinning disk, relatively the same. And it gives you this 2-3 times boost in performance, basically with plug-and-play option. But if you're looking for 200-300 times boost in performance, flash is not an option. It was never designed for it. We'll never give it to you. So the RAM is about the only option if you really need to have an order of magnitude performance increase or more. So flash is fast enough. Yes, it's fast for some applications. It's slow for others. You have to check and see. But typically, if you're already looking at memory computing systems, you kind of already know that flash would not solve the problem for you. The last one I want to talk about is only for caching. And we're actually going to talk about a little bit down the road. But fundamentally, the caching was the first use case for memory computing. And it's always been this way, right? I mentioned to you that 40 years ago, we had caching. The minute we had the first external system for storing data, external storage system, we almost, maybe next year, maybe next 5 years after that, we had first caching application. Somebody figured out that, we may need to keep some of the data closer. But today, basically, it's still an important use case. There's plenty of use case for caching, but today it's a low-hanging fruit, and most, if not all, memory computing systems, apart from very rudimentary, very simplistic ones, most of today modern in-memory computing systems provide a lot more than just the caching. In-memory data grids and memory data fabrics provide dramatically more functionality. And the reason for this is because you guys, anybody who's using memory computing, demand this. I mean, the memory is becoming a system of records for a lot of applications. Once you have that as a system of record, that's the use case. You need to have SQL, you need to have MapReduce, you need to have MPP processing, you need to have key value access, you need to have a lot of different things, transactions and whatnot, and streaming and Hadoop and Spark integration, all of those different functional areas that go way beyond just the caching. The caching is there. All the systems in the world, when it comes to memory computing systems, provide cache. This is a low common denominator. But typically things, go way beyond that. So let's talk about some of the product categories. Now, let's be clear. There's probably, I'm mentioning 4 here, but there's probably another four we can mention, like, memory analytics and memory BI systems. We're not really, talking about those today. We're talking about what, traditionally, historically, we call middleware for developers. So we're talking about memory options, the memory or DBMS, the memory data grids, and memory data fabric. And I'll basically quickly mention it here, and we'll talk about each one of them individually, and pros and cons about them. This is actually the important, if you're really looking for a selection of a memory computing, this is the important consideration, which type of product you need, because within each category, there's multiple types of products as well. In-memory option. So what is it? So typically, in-memory option is something you can basically buy up and enable in your traditional databases. The 2 options here would be, probably more options, but the two most popular options is the in-memory option for Oracle database LC, and there's a similar in-memory option available in Microsoft SQL Server. What they allow you to do essentially is they allow you to turn on some of the optimizations of keeping either indices or tables or something in RAM and not flash into the disk. And that's just that. Basically just an option to an existing database. That's what it is. And we'll talk about it in more details next time. In memory databases or memory RDBMS, this is the bona fide databases built with memory as the main storage layer. This is different from the options. Options, basically a traditional disk databases, but just having an option to pin certain tables or certain data structures like indices and metadata into the RAM. In-memory databases essentially are memory only. They may use disk for backup, whatnot, but typically in-memory databases use memory as the system of records. The examples there, NetSQL will only be SAP HANA of that nature. The next on the list is in-memory data grids. This is actually the first, in-memory data grids are the first purpose-built middleware for in-memory computing. They're not just a database with disk replaced with RAM, but those are from a ground-up built systems to support this new type of data storage and processing called in-memory computing. We'll talk about them. There is a large set of vendors and projects that actually play in this area. Hazelcast, Gigaspaces, Gemfire, and Apache GLF now, and CitySpend, Oil Coherence. Naturally, GridGain can play in this, and Ignite as well. Next on the list, and last we're going to discuss, is in-memory data fabric. Now, in-memory data fabrics are kind of natural extension of data grids. And the difference there is kind of more strategic reach of functionality than just the data grids. And the 2 products that are actually in this category is the Terracotta and Apache Ignite or GridGain, which is the enterprise version of Ignite. So, in the next couple of slides, we'll talk about each of these options individually. Now, let's talk about in-memory options first. So, in-memory options. As I mentioned to you, the key characteristic of that is that it's a feature on an existing database. It's ideal when the only thing you can change within your system is configuration. You cannot change the database. You cannot change any of the applications. You cannot change anything. It's the most plug-and-play in memory computing option, if you will, available to you. literally just spend some money buying this option if you don't have it for Oracle or Microsoft SQL. I think EDB2 from IBM has a similar option as well. And some of your tables, some of your processing will go fast. How fast, I do not know. It really depends. You probably don't know either until you test. But this is basically the option. And I keep repeating the word option in multiple contexts, but this is the option if you cannot change anything other than just the configuration of your database. Often enough, by the way, we don't even consider this to be kind of part of in-memory computing. But those companies spend millions of dollars of marketing these features as part of a memory computing trend. So I'm mentioning it here, but really, it's in my opinion, rather not part of in-memory computing. It's literally a optimization options that's available in the particular products that you can turn on off, and see what works and what kind of performance increase you can get. So as I mentioned to you, all the configurations required, no API changes, no port changes, no data migration, none of that. You basically just have a database and continue to use that. Certain things will just go fast. It's actually the least interesting option, but in my opinion, actually, but I'm biased here. So in-memory databases, this is the first area where I think we can truthfully say that we're talking about in-memory computing option here, or solution or application system. So in-memory databases is basically database with purpose built with in-memory being the storage layer. So when does it make sense to use something like this? Well, it is a clearer choice if you only need SQL. If SQL is the only thing you need, and if you can change the database. Again, very strict requirements to use that category. You only need SQL, and you never will need anything other than SQL. Right? No streaming, no MapReduce, no MPP, no Hadoop, no Spark, just SQL. And in the same time, you have an option or ability to change the database. If you can do that, and you only need SQL, in-memory database is a good option. So naturally, some level of refactoring of your SQL code may be required. Because, for example, if you're moving from Oracle to MySQL, to MemSQL, for example, then you'll likely need to change some of the SQL code. Naturally, like VolDB, for example, would not support Oracle PL SQL. So some level of refactoring may be required. Sometimes it could be pretty significant. What also important is that you need to migrate the data and introduce new database. That's the thing on your organization could be either a non-issue if you're a small startup and you can just switch database on the fly if you need to, or it could be a massive political issue if you're a large organization. So this is one of the biggest impediment to use in-memory databases is that you really have to migrate the entire database to a new infrastructure. It can be very, very prohibitive because not only databases exist by themselves, there are multiple different systems attached to it, and that could be problematic. On the architectural downside of this, databases do not scale. That's a known fact. It doesn't matter if it's a SQL database on disk or SQL database on RAM. Databases, because of the SQL algebra, what's behind the SQL essentially, joins don't really do well in a scale-out environment. So that's an area to consider. Databases do not scale. You can grow a database on a single machine, maybe on 2 machines and 3 machines with just a partition replication, but you cannot get this traditional kind of massively parallelized processing on traditional databases because once again, typically joins don't scale out at all. Well, on any kind of sizable data sets. On a small data sets, everything works perfectly fine. The minute you basically have a data set spread in terabytes, database choke. So that's basically good and bad about in-memory databases. What's really good about them, I mentioned what is actually good about them. The good about them is that you can still basically use your SQL skills. Those are full bona fide SQL databases, and if you don't need anything beyond that, and you can really deal with the data migration and change database, they give you a sizable performance increase with without a need to change your mindset or adopt new programming skills and new languages and whatnot. Let's talk about in-memory data grids. So data grids, as I mentioned, as they're the first, I call minimal bona fide AMC category of product. They were built, relatively recently from scratch, architecturally from scratch, as the a purpose-built middleware for in-memory computing. One of the biggest negatives about in-memory data grids, in-memory data fabric, by the way, is that they will certainly require certain level of. This is not a plug-and-play deal. You have to change the way you store data and you retrieve the data and you process the data most of the time. Sometimes it can be pretty simple if you already have an architecture that's conducive to that. Sometimes it can be fairly laborious. If you have a traditional SQL-based system and you want to move it to a completely new world, some data grids support SQL. That may not be an issue. But if you move into a product that doesn't support SQL very well, and there's quite a few of them, and you're currently a SQL-heavy system, refactoring can be pretty heavy in this sense. So typically, data grids provide a key value access and some optional limited version of SQL. What's really dramatic about in-memory data grids, in a positive sense, is the performance. Performance is the key, the reason that people actually go into this sometimes heavy refactoring to gain that speed. This is the first middleware that can give you a 2-3 orders of magnitude performance increase comparing to the database options or in-memory databases. So in-memory data grids is probably the key category. It was the first purpose-built in-memory computing middleware, and that's the foundation on which the in-memory data fabrics are built as well. So the last category is in-memory data fabric. They are built on top of in-memory data grids. So just to be very, very clear. But it provides more strategic view on in-memory computing processing. In a lame terms, it basically gives more features, more integrations, and really emphasizes across NoSQL and SQL level processing. So if you look at in-memory data fabric, you will find a file system interface to in-memory. So you can view the in-memory as a file system. You obviously have all the basics of a data grid, like key value store and transactions. But you also have a full-blown SQL support if you need it. You have integration with Hadoop, things like Spark integration, streaming processing as well. So the in-memory data fabric, the word fabric is alluding to the fact that it's a general purpose framework or platform, just looking for synonyms here, that it can do a lot of different things with data that's stored in memory, not just basically caching or key value access, but basically any type of use case you can imagine you can do on a memory data fabric. And that's the fundamental difference between memory data fabric and data grids. In terms of performance, they provide exactly the same performance as data grids because they're all based on the same type of technology. Memory data fabric are not about outperforming data grids. They're about out-featuring data grids, providing more features, more capabilities than just the data grids themselves. So if you look at the summary, so let's look at it again and kind of summarize where would you use each in a category. So in memory options, they're kind of marginally improving performance of existing database. Again, the key here is marginally. You're really going to get maybe 2, 3, 5, maybe 10 times at some specific tables and some specific use cases. The good news is that there's a plug and play deal there. You really do not have to do anything. Just you just turn this feature on, and you have this capability right away. No data migration, no code change, no API change, nothing. InMemory Databases. Next option here. You're still going to live within a real database. It's a database. You still have a SQL-only databases. But those databases built purposely on a memory storage layer. Therefore, they provide you much better performance increase, generally, but may require a sometimes minimal, sometimes significant refactoring, depending what kind of dialect of SQL you would be using. The negative side of database is still database. It still doesn't scale. It still has a limitation of SQL only. InMemory Databases is probably what you would consider to use most of the time, at least in the last 5 years. It's ideal for greenfield projects. Ideal when you can basically have a greenfield project where you can change the data access architecture in your applications. And it's about the only option when you need to get, several orders of magnitude performance increase. That's a very clear gating factor. If you look at your system today and say, gosh, we need at least 50x performance increase. There's nothing else in the market today. There's no CPU you can buy. There's no RAM you can increase. There's no computer you can buy. There's no language you can rewrite on. There's nothing you can do. The only technology that is available today is to use memory computing. Move the data into the RAM, do it in a smart way, and you can get the 50x. So it's a very clear gating factor. To have this performance requirement, data grids or data fabric is the key. Now, the data fabric is what, I would have my own bias, but that's what I would recommend because it's based in data grids. Every in-memory data fabric has the data grid in it. It has the same performance benefits as a memory grid, but it gives it dramatically more functionality. And you don't want to pick a product that would require you to do a significant amount of factoring and then at the same time lack certain features. Data fabrics are at the front here today. There are next generation of memory computing middleware, and that's what I would personally recommend to use. And by the way, naturally, Apache Ignite is the forefront of the memory data fabric technology, and that's the open source Apache-based product, which is becoming a standard in this area. So let me summarize some of the key features. And again, this is the area where I can be very biased, and I don't want to be too biased about it. So as I mentioned at the very beginning, I'll mention some of the key features you guys have to be on the lookout. Not every one of them may be needed in your project, but it kind of makes sense to inquire about them and see what kind of support you have for those, because those are basic ones that you probably end up needing one way or another during the life cycle of your systems or applications you're building. Again, you can get line-by-line comparisons, in many different places. You can find them on GridGain.com, on Apache website, or all our competitors' websites as well. So what are the key features? I definitely recommend to look at scale-out and scale-up possibilities on those products. It's kind of very important. It looks kind of high level, but it's not. The scale-out means can I run this middleware on 1,000 nodes? And will I get a normal linear performance increase? The scale-up means this on a $5 million Fujitsu supercomputer, because sometimes those are options. And you can very easily build a system that works in one scenario but doesn't on the other, or only works on, on the Fujitsu, doesn't work on the scale-out bar. You don't know what system is going to run. You don't know how your system is going to be deployed. So I would highly recommend asking this question and testing and asking your vendors or projects, can they cite any examples of these scale-out and scale-up deployments? It's very, very important, especially today. When it comes to memory data grid, naturally, some of the key features is the fault tolerance and high availability, transaction and SQL support. Those, I would probably say, spend most of the time looking at these features. Data grid functionality is the one you're going to use most of the time, even in the data fabrics. Data grid is something that's at the core. That's where you store data. That's where data resides. you need to understand all the fault tolerance features, data replication, data durability, how is high availability is managed. What if you have, many reads coming into for the same key, for example? How is it managed? What type of transactions support? It's a very, very big deal. I highly recommend testing against transactions because this is the one area where products differ dramatically in performance. Some products don't even support transactions at all. They only support, for example, non-transactional behavior. And what happens when your system needs to have transactions? What happens if in your system you need to have a single transaction that spans memory, database, and JMS message, for example? If you don't have it from the vendor, you're basically out of luck. There's no way you can roll out your own in a sensible way. So transaction support is very important. Probably number one feature that I would recommend to you to look at is SQL support. There is a massive misunderstanding. Why do we need to have SQL support in memory systems that are traditionally built as a NoSQL systems? The problem is very simple. Indices. SQL is ideal to work when you cannot afford full scan. Indices are the key feature of why SQL is important. If you have terabytes of data, you need to find all the records with the name Nikita. If you don't have SQL, guess what? You're going to have a full scan. And you can obviously imagine what the full scan means in terabytes of data. It doesn't matter whether it's a memory or disk, it will take minutes. If you have indices that are maintained by the system, and they have a SQL capabilities to actually do the basic select statement using the indices that's supported by, you can still query terabytes of data in a sub-millisecond fashion. That's the fundamental reason why SQL is so dramatically important. And naturally, you're looking for a full SQL support. You're not looking for some kind of optional subset or whatnot. You're looking for a full, normal SQL support, like SQL 99 standard. So this is basically one of the key features what you need to look in data grids. Cross-language support. Naturally, if you're in a big shop, things like Java, .NET, and C++ are must-haves. Some of the products would have Node.js and the REST interface. Most of them would have PHP and Python. Just look for as many as possible. Typically, open source projects would have a big ecosystem, and it's mostly most vibrant ecosystems of different drivers. I always keep saying, look at MongoDB. It's just a different example of database, but look how many drivers MongoDB has. And that drives a lot of usability, drives a lot of safety of selecting this database over the other competitors. If you're in the compute side of things, look at the ways of supporting all these different abbreviations, MPP type of processing and MPI, which is method passing processing. Look at HPC and RPC type of processing as well. In memory streaming, if you're in streaming, if you're looking for this use case, look at what is in memory streaming capabilities exist. Typically, we'll find that only in memory data fabric. From enterprise level features, look at security manageability. Naturally, those sometimes come in enterprise version. For example, in GridGain, the auditability, security, manageability comes in enterprise version of Apache Ignite. From a deployment standpoint, I would look at Mesos, Yarn, and AWS, Google Compute Engine. Look at those options if you're looking in the cloud. Typically, you'll find at least one or two in the projects. Sometimes you find all of them. Again, open source projects like Apache Ignite would have a significant sway and advantage here because of the ecosystem and in how these projects, interact with Apache. And if you're looking at, and if you deal with a big data stacks, natural integration with Hadoop and Spark would be an option for you to check out. Again, Apache Ignite is probably the best option right now for Hadoop and Spark integration. It has a direct integration with Spark and Hadoop. It's pretty good, pretty interesting stuff there. So I know we're kind of up against the timeline. I'm going to spend a couple of minutes just to basically key use cases and apps. Again, if you're on this webinar, you probably know all about it by now. But typically, we're finding in memory computing systems used in a variety of different financial services financial services use cases, automated trading systems, real-time trading position, risk analysis, high volume transactions, ultra low latency trading, things of that nature. We started to see a lot of the hybrid OLAP and OLTP use cases where people trying to do the analysis on operating data sets. It's a very interesting use case. Online mobile advertising, again, very natural use case for memory computing systems because you have lots of data and basically have a hardcore select to make a decision. Real-time data analytics, again, very similar to financial services use cases. Online gaming, where actually, as an example, Apache Ignite actually used in some of the backends in some major Sony games. Very interesting use cases. One of the use cases that actually crosses all kind of domains and industries is a SaaS enablement. Very interesting use case because when you're going from kind of in a client server pro customer installation to a SaaS-based system, so all of a sudden the same infrastructure, same software now needs to support dramatically more users. And in-memory computing is about the only option again. As you can probably heard me throughout this presentation, I keep saying that in-memory computing often is the only solution to gain that performance edge. So SaaS enablement is what we kind of seen almost on a weekly basis when it comes to GridGain. So Dane, I think it's the end of my slides. We can probably switch to Q&A at this point. I'm just a little bit over time.
Yep, that's right. And we do have a few questions for you here, Nikita. So let me just go ahead and run a couple of these by you. Here's the first one. Do you support running in a platform as a service runtime environment such as Cloud Foundry? They specified, but maybe you want to speak to any other platform as a service that we're.
Yeah, I think
it's about as nice.
Right. We actually have a client who is pushing for a Cloud Foundry support, so that's going to be happening rather quickly. I don't think we have any specific integration right now in other past players, but Cloud Foundry will be happening literally very, very quickly. We're probably a couple of months away from having support for that.
Okay, excellent. And they were asking specifically about Cloud Foundry. Any others that are worth mentioning?
I'm not aware of any others because literally the best way here is to look at the dev list for Apache Ignite. And if you have an idea, suggest over there. I mean, this is the community-driven project. So if you have an idea for one, just suggest and see what community says. I do know the Cloud Foundry is very much on top of the list here. So Cloud Foundry it's in fact happening already, and will be released quickly. Others,
okay.
Guys can suggest on the community lists in Apache.
Okay, great. And by the way, for all the attendees, there's still time to get your questions in here, and hopefully we can get to all of them. But so here's another one for you. How about times 10 in-memory database from Oracle? Is this truly an in-memory RDBMS?
Yes. By the way, I should have actually added this as an example. Yes, it's the same category as MemSQL, VolDB, SAP HANA, or times 10, and I probably missed one or two more. Yeah. We haven't seen times 10 in a while because it was acquired by Oracle 15 years ago. We do see more of a MemSQL, we do see more SAP HANA and VolDB, but yes, times 10 architecturally belongs to the same category.
Okay, and here's another Oracle question. Where does Oracle's Exadata fail in terms of the types of in-memory categories? Oh, I'm sorry, it's not fail, it's fall. Where does Oracle's Exadata fall in terms of the types of in-memory categories? Big distinction.
I think it fails too. I think one area it is obscenely expensive for what it does. It is still a database-driven solution for memory computing, and I can tell you for a fact that something like Apache Ignite will outperform it by a factor of 10, if not by a factor of 100, in the same time on the hardware that costs 100 times less. So it's probably, Oracle is a unique company. It has strange technology that is massively overpriced, and they're still selling it. So there is a market for it. But I can tell you, and I don't want to throw in too much bias here, but I can tell you from a GridGain perspective, the company that I founded and work for, is that we routinely replace Oracle products in companies, like literally one a month. And we almost never heard about Exalytics and Exadata. I know it exists, obviously, but I don't think it really, spoke in the same sentence as other products. There's other products in the market that, deal with in-memory computing. Not only us, by the way, not only GridGain and Apache, there's GigaSpace, there's a Hazelcast. Oracle has its own coherence product that's much more closely to that. Those we can hear, and those we, friendly compete in every day. But there's big irons from Oracle. We almost never hear about them.
Okay, thank you. And then here's another one. Is there a GridGain API for Node.js, or is it REST API that's used?
Actually, excellent question. The Node.js probably will be released literally within a month. It's been in the works for a long time. You know what? You just have to look at the Apache Ignite website, see if it's already been released. It might have been released because I know there's quite a few guys been working on Node.js driver. So if it's not released, it's definitely available in some of the builds already. And it's definitely going to be released in some kind of capacity in the next month or two for sure.
Okay, great. Okay, and here's another one. What would be the approximate maximum number of physical machines for a GridGain cluster above which performance of a large GridGain partitioned cache, say above 1 terabyte, would start degrading, say under a large number of reads and writes into the cache? Did that make sense?
Yes, and my answer is I do not know. We do have our largest customer running us on 2,000 computers, 2,000 servers. They're running us in production. Beyond that, we haven't tested yet. So I can only guess. I don't think architecturally we have any limits there. We don't have like a limit of nodes or anything like this. But naturally, once we go from 2 to 10,000, something will break, and something will have to be reconfigured or something like this. So the honest answer, I do not know what the limit is. 1,000 computers, I'm pretty solid. It works pretty nicely. If you ask me 10, 20,000 computers, I do not know. But then I ask you back, what kind of use case do you have that needs that type of large cluster?
Okay, great. And here's a question that I can answer, actually, which is, do you have a feature comparison sheet with XAP from GigaSpaces? So first of all, I'll say if you go to the GridGain website and go into the resources section, you can find a few feature comparison documents there. A couple of those are actually here in this presentation, and you can get them from the resources area. GigaSpaces is not one of them, but if you'll send an email to sales@gridgain.com, we do have those available, and we can send those over to you. So that's how you can get that particular feature comparison. It does look like we're up against the end of our time. I don't think we'll have time to take any more questions for this one. So I want to go ahead and wrap up for you guys. I want to thank Nikita for all that great information, and I hope everyone got a lot out of today's presentation. As we sign off, I did want to remind you that you can download the PDF of today's webinar, as well as the feature comparisons that I just mentioned from the resources section. I also wanted to mention, for any of you who are here in the Silicon Valley, that GridGain is hosting a meetup in Sunnyvale on December 16th. where Nikita will be presenting along with other thought leaders in the in-memory computing space. So that's a great opportunity to meet Nikita in person. You can get the details of that at the URL shown here, and that's on the PDF of today's presentation. And of course, you can get the details through the GridGain website as well. So we'll hope to meet some of you in Sunnyvale. Thanks again for attending today's webcast, and have a great rest of the day.